Hello, my name is Garon Smith. I'm a professor of chemistry at the University of Montana. I'm going to share with you some of the ways that I have tried to bring SENCERized type big social issues into my large content-driven introductory chemistry course at the University of Montana. The course that I teach is called Chemistry 121, Introduction to College Chemistry. It's the largest class on campus. It has about 700 students in the fall and about 300 in the spring. It's a required course for applied science majors. These include forestry and wildlife biology, which are some of the most prestigious majors at the University of Montana because students come to Montana to study our wildlife, the grizzly bears and the elk and the wolverines and the mountain goats. It also includes field botany and field zoology students, environmental studies, which is a policy and advocacy program, all of the allied healthcare fields like nursing, physical therapy, medical technology. It includes athletic training and exercise science, forensic anthropology. So it's a required course for many different majors. Because of that, I have a certain content I'm expected to cover. It's the first half of a year-long GOB course. In chemistry, we use GOB to stand for 1/3 general chemistry, 1/3 organic chemistry, 1/3 biochemistry. I teach the G and start the O. My colleague finishes the O and does the B as the second semester part of the course. And this satisfies half of the natural science requirement for our general education program. So besides the required courses of study that put people in my class, I also have students from other majors that take my course because they want to do the chemistry course because it's gotten to be quite popular. In fact, it usually shows up as #1 on the list of courses you have to take before you leave the University of Montana. So it's a big class. The course enrollment is 600 to 700 in the fall, 250 to 300 in the spring. The main goal of my course, I don't really tell the students, is to have the students finish the semester feeling good about chemistry. Most of the time, students are dreading their required chemistry courses. And what I would like them to do is get to the end of my course and say, oh, that was pretty good course, interesting stuff, useful material. Maybe I should think about taking more. So that's my goal in the course. But I also have to have as one of my goals to maintain the course content as required by the department and campus sequence expectations so that they don't say, oh, you're not holding up your end of the bargain of what you're supposed to be doing in that class. But most of my colleagues don't know what I've done to the contents of the course because my students eventually come out of the end of the course having the same content that they would have if I would have taught it in a traditional way. Another one of my goals is to engage my students in local community issues. I would like them to become engaged citizens and learn how to do that. So I make them pay attention to what local community issues are during the semester. And I'd also like to empower them to take action on things that are bigger than local community issues that might have national scope or even international scope. They can't necessarily be active in something internationally, but they can still have an impact on it. I try to show them how to do that. Here's a bar chart of how the course enrollment has grown. I started attending SENCER meetings in 2001, and you can see that the course has grown fairly steadily since then. We've had it sort of plateau in the last few years, but it's generally been a very popular course. Like I say, it's the largest course on campus. And in the fall, I have to teach it twice a day because there isn't a lecture hall big enough to hold everybody at once. I teach it at noon and then again at 4 o'clock. Sometimes students come for both lectures just because they wanted to hear the material a second time. What I do is try to use all of my examples for teaching different concepts or working problems. I pick my examples to come from local, national, or global issues to supply some motivation for why they might want to learn the particular concept we're covering at the moment. And I want them to understand how chemistry is a part of almost everything that we do as a society in one way or another. What I do is start different threads of storylines and then revisit them throughout the semester. As we go from one chapter to the next, I say, oh, now that we're in this chapter, we can look at this aspect of a particular problem. And that lets me show the disciplinary richness of some of these social issues. They wander outside of chemistry, but as we go through the chapter sequence, we can look at different aspects of them. I should say that this is not a pure SENCER course in the way that some SENCER courses have been designed. So a pure SENCER course takes the name of the course and even changes it to what issues you might be looking on. I don't do that. The reason that I have taken the approach that I do is because I have to teach Introduction to College Chemistry. I can't change the name of that course, really. It wouldn't do to have a fancier name on a transcript, because students going into nursing programs have to have 2 semesters of introductory chemistry. So it's a way I can take what looks like a standard course and change its content to be what I think is much richer. Here's a graphical representation of the pure SENCER course. It would be called Smoky Skies and Polluted Waters in the West. See, a nursing school isn't going to accept that as a course title for the chemistry requirement that a student would teach. And if this were the title of my course, then we'd talk about western wildfires, we'd talk about cyanide heap leaching, which is a way to process gold ores, we talk about pulp and paper mill emissions, we talk about diesel spills. And as we talked about these different topics in the pure SENCER approach to a course, we would uncover the content as opposing to discover the content. And so by the time we delved into the issues that are listed under the smoky skies and polluted waters, by the time we covered all those issues, we would have covered the traditional topics that are in that introductory chemistry course, but we would have done it from the outside in. So I call my model the Trojan Horse model, because the course title is the same, the textbook is the same, it looks like it's the same course, it gets led into any acceptable sequence of courses that are required for a major, but it's got a hidden something inside it. What it does is it allows the SENCER ideals to be incorporated into an already existing course that doesn't require new course approval. If you change the title of the course, you've got to go through a whole approval process on our campus. But doing it the Trojan Horse way, it's still called Introductory Chemistry, Chemistry 121. So it's very easy to do. And you can do it incrementally. You don't need to change your textbook. You just need to change what you talk about in classes. This is easily something that could be done in the content-driven courses for majors. If you want to major in chemistry and get an American Chemical Society certified degree, there are certain courses you have to take. And again, this lets the course meet the requirements of the American Chemical Society, but its content can be a lot richer. Here's the diagram that I use to sort of illustrate what the Trojan Horse model looks like. It's got the sequence of chapters as the target pattern. Atoms is one of the early chapters. Then they go to chemical bonds, intermolecular forces, chemical reactions. That's the sequence of topics in the textbook that I use. But overlying this target pattern are these flower petals that show some of the different storylines that I pull into the course. These are issues of things that belong in that wildfires and polluted waters in the West, and are enrichments to the normal chemistry content. So for instance, in my course I talk about detecting buried landmines and terrorist bombs using honeybees. I talk about the cyanide heap leaching, talk about western wildfires, talk about the pulp and paper industry because we have a big pulp and paper mill in the same city as the university is. I have a lot of Native American students. They're our leading underrepresented minority in our campus culture, and so I celebrate some of their practices in the chemistry course. And I also work quite a bit on environmental problems that have come from diesel spills or other sorts of toxic materials being released. So I can use the same textbook. It's just that instead of using the textbook examples, I pull my examples from these different themes of issues that are important. So let's look, for instance, at western U.S. wildfires. The University of Montana is located in the middle of a host of forests. We have forests surrounding us on all four sides, and periodically they burn. That seems to be more frequently recently. People attribute that in some cases to global climate change. So what do? In chapter 1, when I talk about chemical versus physical changes, I relate it to wildfires. In chapter 2, I talk about incandescent flame emissions, soot particles glowing. In chapter 4, we write chemical equations that have to do with the combustion reactions, and we talk about the percent yield of reactions, how much of the combustion leads to carbon dioxide and water versus other things. In chapter 5, we talk about phase changes. In chapter 6, we talk about how smoke particles scatter sunlight. And in chapter 7, we talk about heat of combustion. So what you can see there is 6 out of 7 chapters are going to include part of the story about western U.S. wildfires. And that means I can talk about it 7 different times during the semester. Here's the way I cover it in the first chapter of the textbook. The first chapter talks about chemical changes versus physical changes. In chemical changes, chemical bonds are broken, the atoms rearrange themselves into new compounds. So new chemical bonds are formed. An example reaction would be propane, C3H8, reacting with molecular oxygen, O2, to form carbon dioxide and water vapor in a perfect reaction. So see, we start out with bonds between carbon atoms, bonds between carbons and hydrogens, bonds between oxygens. And in the end, our products have new bond arrangements. We now have carbon-oxygen bonds and hydrogen-oxygen bonds that weren't present in our original materials. Physical changes don't involve changing the nature of the chemical compounds. They're associated with changes in state. Are you a gas, a liquid, a solid? Are you dissolved in a solution? No chemical bonds are rearranged. If you look at water, freezing to ice, it's H2O before and it's H2O afterwards. It's just the phase that's different. And we can take that ice and melt it back into the water without rearranging any chemical bonds. The same thing happens with sugar. Sugar will dissolve into water, but we didn't break any chemical bonds. Whole sugar molecules are floating around there. When you let the water evaporate, the sugar will come back. If you do it right, you can get rock crystal sugar candy. So it's C12H22O11 before and the same formula afterwards. So how about a burning candle? This is an example of a clicker question that I put into the class. I actually don't use clickers anymore. A lot of times I have the students vote by standing, but it's good to give them a chance to think about things, see what their classmates are responding. Also lets them mentally reset a little bit. They don't have to take in information, they have to think about it. So is a burning candle a chemical change, physical change, or both? In this case, it's both. In fact, I've come to believe that it's very difficult to find things that are purely chemical or purely physical unless you are really careful about it. I found this by asking questions, is this a physical or chemical change on exams, and then having students come up and say, yeah, but what about such and such? So let's look at when a candle burns. It's like most world processes, it involves both kinds of changes. Heat from the flame melts the wax, and it also pyrolyzes it, breaks it into shorter chunks that then are in the gas phase. And then the vapors burn with oxygen to form carbon dioxide and water. So there's two kinds of chemical changes going on: pyrolysis, which is breaking long chains into shorter ones, and then rearranging the chemical bonds to make carbon dioxide and water. Let's look at this in very simplistic PowerPoint diagrams. Here's a candle made out of paraffin wax. If we're going to burn it, we're going to bring a match up. We light it on fire. You can see that why art wasn't my major. And what we'll see is that heat from the burning match causes some of the wax to melt, some of the wax that melts then pyrolyzes, and you get, instead of an 18 carbon chain wax molecule, you start getting shorter fragments that are 2 to 5 carbons long that are in the gas phase. It's those gas phase fuels that actually catch on fire. We're also going to use heat from the match to break the oxygen-oxygen bonds in the molecule and to break down those smaller chunks so that the carbons and the hydrogens can hook onto the broken oxygen bonds. Once we get the flame established, it's really a ball of hot fuel gases around the flame, around the wick. The wick isn't burning, the combustion is taking place in the gas phase. The actual chemical reaction where we're making CO2 and water, that's in the blue line around the outside edge. Let's go in for a closer look to see what the flame cross-section looks like. The reaction zone, where the fuel vapors and O2 come into contact, involves taking something like maybe ethene, C2H4, and reacting it with an O2 molecule. What we get out of that is CO2, which has carbon-oxygen double bonds, and a water molecule. They dissipate into the turbulent airflow around the top of the flame. So if you look at a picture of pine litter burning, such as would happen in the ground part of a western wildfire, you can see that the flames are not down on the solid needles, they're in the area above the needles. Now, many of the students in my class have their summer income derived from being wildfire fighters. So all of the forestry and wildlife biology students are very interested in this aspect of chemistry. The fact that flaming combustion takes place in the gas phase is even more pronounced in this picture. It shows a couple of firefighters using a drip torch to start a backburn. You can see the flames are probably 30 feet high, and certainly the drip torches aren't burning solid material 30 feet above the ground. Those are volatile gases that are actually doing the flaming part of the combustion. How about the water that gets produced as a product of combustion? Well, in a really big fire, that water vapor is lofted high into the air where it cools off and forms water droplets. So fires can actually generate their own clouds that have not just smoke, but also little droplets of water in them. They make rain clouds, and you can have thick, sooty drops come out of these clouds that build up over a fire. You say, oh wow, look at it, it's raining, good. No, it means the fire has made a run, and the hot gases of water vapor are going so high they're cooling off and condensing into rain. This is a close-up of what it looks like during a run of a fire where we're getting clouds building up. Here's a picture taken from about 30 miles away. You can see a huge cloud that forms above the western wildfire. This was in 2006, the Derby Mountain Fire in south central Montana. After talking about gas phase burning, where the flaming part of the combustion takes place in the gas phase, just for fun, I stop and I do a little demo. What I do is take a mixture of water and alcohol and dip a dollar bill in it and then light it on fire. And then I talk about the fact that solutions can minimize their surface energy in two ways. They can either bead up, or they can take in a solution the material that has the lower surface tension and put it to the surface. Well, in a water alcohol mixture, alcohol has a lower surface tension, so that when I take a dollar bill or a $10 bill or a $50 bill or a $100 bill I sometimes bring, when I dip that in the mixture, when I then hold it up, what we'll find is that the very outside layer of the liquid coating the bill is actually a thin little layer of alcohol, and it's vaporizing pretty well. When I light it on fire, that outside thin little layer of alcohol catches on fire. There's a water alcohol solution that's protecting the bill from the flame that's burning on the outside in the gas phase. The longer the alcohol flame burns, the more alcohol is pumped to the surface, and eventually the system runs out of alcohol. You just have a layer of water still protecting the unburned bill. So my $100 bill is never in danger when I dip it into the solution and light it on fire. Here's a little bit of an example of how I bring Native American culture into my courses. Throughout the semester, I select sample problems that illustrate some of the chemistry behind traditional practices of our Native American peoples. This is a way to celebrate cultural diversity within a science setting, and I can noticeably see the Native American students in my class suddenly perk up and pay particularly close attention. This is from chapter 4, where I've just introduced the concept of moles and formula weights. So what is a mole? A mole is a counting term for chemists. It's the same kind of term as a pair. What's a pair? 2 of anything. What's a dozen? 12 of anything. What's a gross? 144 of anything. What's a mole? It's 6.02 times 10 to the 23rd of anything, or Avogadro's number. It's a very big number. It's technically defined as the number of atoms that are in exactly 12 grams of carbon-12. It's a convenient lab measurement when you're going to try to figure out how many atoms or molecules you've scooped up and put into your solution or into your beaker. It usually provides gram scale quantities if you're talking about how much is a mole of a certain kind of atom or a certain kind of molecule. It's the second number that is found on an element square on the periodic table. The first number is the atomic number, the number of protons in its nucleus. The second number you're going to find there is its atomic weight. For this course, carbon is very important. Let's look at carbon. It's element number 6. If we expand its square up to see more information, the next number we'll invariably see is 12.011. This says that on the Earth, that's how many grams of carbon it takes before you have a mole of carbon atoms. If we did this with sodium, it would be 22.9898. If we have molecules and compounds, we simply add up the individual atomic weights to get the formula weight. We're going to multiply the atomic weight by the subscript in doing these summations. So if we wanted to talk about 1 mole oxygen atoms, it would be 15.9994 grams. If we have oxygen molecules, O2, we have to multiply by 2, so it's about 32 grams. If we have ozone, which is O3, we'd have to take the atomic weight times 3. So one of the first molecules I have the students calculate the formula weight of is vanillin, C8H8O3. Here's a picture of its structure 2 different ways, a line angle drawing on the left and a space filling model on the right. I just talked about trying to know whether molecules are polar or not by seeing if they have phone call atoms. These are the highly electronegative atoms. Oxygen is one of those. If you have oxygens asymmetrically distributed in the molecule, it's going to be polar, and it should dissolve into water pretty well. So what's the formula weight of vanillin? We'll take 8 times carbon's weight, 8 times hydrogen's weight, 3 times oxygen's weight. When we add those all up, it turns out to be about 152 grams. Now, why did I pick vanillin? Well, because the Native Americans like the smell of vanilla too, and they used to find it in ponderosa pine trees, and they would peel the bark off to get to it. These are called peel trees. So after a long winter time where they were eating dried berries and dried or smoked meats, the Native Americans would wait for the sap to start flowing in the pine trees to make a sweet treat. Remember, the sap has sugars in it. So they would peel the bark from the outside of ponderosa pines and eat the sweet cambium layer. It's rich in starch, sugars, minerals, fiber, and vitamin C. But because it has vanillin, natural vanilla in it, it tastes like cookie dough. So this was a real tasty treat to the Indians, and they would peel the bark off and eat it to enjoy a different kind of food after a long winter time. If you walk up to a ponderosa pine on a bright sunny day, you can smell that vanilla just by sticking your nose into a furrow of the bark. Here's a picture of a ponderosa pine trunk. See those cracks? Just insert your nose there and take a deep whiff. It'll smell like vanilla. Here's a tree in Oregon that was peeled by the Molalla Indians. These are called culturally modified trees, and they're distinguished by having a scar in the bark that's up around head level. Scars from fires usually form right where the leaf litter comes up against the bottom of the tree. So if you've got a scar up higher, it's probably a peel tree. You can find local peel trees if you go to Council Grove State Park off of Mullen Road, just west of Missoula. You can also head south of Missoula to Lost Trail Pass. There's a Forest Service campground called Indian Trees. Why is it called that? Because there's a whole concentration of Indian peel trees that were there. Lewis and Clark noticed this when they came through on their way to the Pacific in their historic expedition. Here are a couple of journal excerpts. Saw where the natives had peeled the bark off the pine trees to obtain the sap and soft part of wood and bark for food. This was from a July 19th, 1805 entry near Helena, Montana. Here's another one. I made camp at 8 on this road, and particularly on this creek. The Indians have peeled a number of pine for the underbark, which they eat at a certain season of the year. This is from September 12th, 1805, Lolo Creek, 9 miles south of Missoula. So see, it's part of our local heritage. After they've done vanillin, I then check them out with a clicker type question. What's the formula weight for ammonia? Here are the atomic weights of both nitrogen and hydrogen. A lot of times I use the clicker questions to help students diagnose what they're doing wrong. Correct answer should be 17. If you picked example 1, or answer 1, what did you do? You added atomic numbers instead of atomic weights. If you picked answer 2, you only included 1 hydrogen. You have to multiply it by 3. If you answered number 4, you multiplied both nitrogen and hydrogen times 3. It's just the hydrogen that gets multiplied. So I use these clicker questions to help them see if they understand what's going on, and if they pick a wrong answer, how they may have gotten to that. Here's a third example of one of my enhancement issues that I bring into the class. Missoula has a big pulp mill. It's called the Smurfit Stone Pulp Mill because of who runs it. And here are some of the concepts that I can cover in talking about this. Lots of the students have family members who've worked there or may work there themselves. People who live in the valley think the pulp mill is the source of many of our environmental problems. They don't understand how it works, so I enjoy showing them how a pulp mill actually works. Here's some of the concepts I get to cover. Stoichiometry, which is from chapter 4. Thermal decomposition from chapter 7. Double displacement reactions from chapter 4. Percentage composition by volume, which is also from chapter 6. Parts per billion, also from chapter 6. Conservation of mass. Some extra topics that I get to bring in because I'm dealing with this in class that are what I call SENCER add-ins, include closed process loops for industrial designs and biomass versus fossil fuel CO2. Not part of your standard chemistry course. It's added enhancements. So here's a picture of the pulp mill. It's a large facility. There are 800 acres of ponds to treat the water that comes out of the pulp mill. Huge piles of sawdust and logs, tall columns of complex-looking processing equipment, and plumes of vapors coming out from all parts of the plant. So I've worked quite a bit with the pulp mill. Some of my graduate students have helped them work on some of their environmental problems. And in working on those, I've put together such a good description of the pulp mill and how it works that the pulp mill said, how about taking this to the State Department of Environmental Quality so they can figure out what we're doing too. So this is extracted from a program I put together for them. The way that they make pulp in Missoula is called the craft process. What they do is they make liner board. That's the outside and inside layers of a cardboard box, not the crinkly stuff in the middle. If you look at a cross-section of cardboard, you can see 2 flat sheets of liner board on the outside and the inside, and then the corrugated medium in between. They don't make the corrugated medium in Missoula, they just make the liner board. Why do they call it the craft process? Well, they want to make strong boxes, and craft is the German word for strong. What do they use for raw materials? Well, they're actually someone else's waste stream. They use wood chips from lumber mills. They use broken, crooked, and undersized logs that can't be turned into nice-looking boards. And they use discarded cardboard boxes. They call them old cardboard containers. So that's what they use as their starting materials. If you look at a picture of the plant from the air, there's the chip piles, there's the log yard with the broken, crooked, undersized logs, and back here that's the cardboard recycling plant. So see, that's their starting materials. Hog fuel, that's the bark that can't be turned into paper either. Most of these starting materials used to be disposed of in less than optimal ways. What happened to them? Wood chips were burned in teepee burners, released a lot of smoke. Logs were burned in slash piles, released a lot of smoke. Cardboard boxes were burned in incinerators. Makes a lot of smoke. I used to go down to the grocery store and watch them burn them because it was a great big fire chamber. It led to particulate pollution for the surrounding communities. Guess what Missoula's leading air pollution problem is? Smoke. Fine particulate matter from combustion of wood waste. Here are pictures of teepee burners. You can see they gave rise to very active columns of smoke. They used to dot the landscape all over the West until the craft process was brought in. Here's a historic one at our local museum, historical museum, painted to look like it's got a fire inside, but it doesn't. I give an extra credit challenge to my students and say, hey, there's a teepee burner on our campus. Find it and email me information about it, and I'll give you an extra credit point. And they say, where's there a teepee burner on campus? I mean, these are 20 feet tall iron teepees. Well, it turns out there's a sculpture on campus that's a depiction of a teepee burner. It doesn't have any sign on it. And people say, when I show them this, they say, I had no idea what that sculpture was. Makes for a fun little scavenger hunt. Although the first time I did this, I got a call from the information desk, and they said, could you please tell us where there's a teepee burner on campus? Remember, I have 700 students. They were being besieged by question after question of where's the teepee burner on the University of Montana campus? If we look at the overall process of making craft paper, it uses a reservoir of chemicals that recirculate. They get used over and over and over again. That's a good sustainable design. They cook the wood chips in white liquor, which is sodium hydroxide and sodium sulfide. That dissolves the wood. It releases the fibers of cellulose, and the leftover material that has some dissolved stuff in it is called black liquor. It's a combination of sodium carbonate and sodium sulfate. That's processed. That's processed in a recovery boiler that burns the black liquor and changes it into green liquor. So they get some heat out of it too. The green liquor has sodium carbonate, sodium sulfide. Using a process called recost, they convert it back into white liquor. So they get to use these process chemicals over and over and over again. It's very economical for the pulp mill, and it's good from a sustainable environmental standpoint because you don't have to keep coming up with new materials to use as process chemicals. I eventually go through the whole plant and show how a craft pulp mill is actually two big closed recycling loops that interact with each other. It's a very good industrial design. More industries should have closed process loops. So we just talked about the white liquor, black liquor, green liquor loop. The second loop takes the material that's made during the green to white liquor transformation and puts it into a second loop, and that's a lime kiln loop. And that becomes the first stoichiometry problem in my course. So see, we're tying the local pulp mill to the topic of Chapter 4 of stoichiometry problems. Here's what the lime kiln looks like. Calcium carbonate enters at the left end into a hot pipe that's got natural gas burning at 1400 to 2200 degrees, and it cooks carbon dioxide off of the calcium carbonate and changes it into calcium oxide at the far point. Calcium oxide is also known as quicklime. So I describe the stoichiometry calculation as a three-step process. We have to go from grams to moles because chemical reactions are written in moles. That's what the recipes are in. Once we know what the recipe is, we can relate how much of one ingredient it takes to make so many grams of a product, or how many other or how many moles of a product, or how many moles of another ingredient it will react with. Then we have to change it back to grams. So there's 3 steps here. And I've given you the information that's needed to get from one piece of information to another. Formula weight gets us from grams of A to moles of A. Coefficients from the balanced equation get us from moles of A to moles of B. So here's what goes on in the lime kiln. Calcium carbonate gets changed into calcium oxide. In this particular problem, calcium carbonate is substance A. Substance A in this kind of problem is the one that has a mass attached to it, 4.72 grams of limestone. Substance B, that's the one that we're going to calculate an equivalent weight for. In this case, it's calcium oxide. So here's the general problem-solving strategy shown diagrammatically. We're going to do the first step, 4.72 grams of calcium carbonate. We're going to divide by the formula weight and get moles of calcium carbonate. So here we are doing the calculation, 4.0472 moles. So we've done the first step. We do similar sorts of procedures to get to the final answer. It says 2.64 grams of calcium oxide come from 4.72 grams of calcium carbonate. Notice that we're giving off CO2. Ooh, isn't that a greenhouse gas? Yep, but this is not fossil fuel CO2. This is biomass CO2 from the wood chips. And as long as trees are being regrown to fill in for the trees that were harvested, this is more greenhouse gas neutral. It's not totally greenhouse gas neutral, but a lot closer than if you're burning fossil fuels. I point out that whatever we release into Missoula's airshed, we have to breathe many times. Most times overnight, we have the cold air sink down to the bottom of the valley, and it pins pollutants down right on top of us. Here's what it looks like on a clear day in Missoula. You can see the campus sitting at the base of Mount Sentinel. Here's what it looks like on a temperature inversion day. That cold, stable puddle of air sits in the bottom of the valley, and our pollutants can't get out. People were worried about what the pulp mill was putting out in the way of pollutants. Well, it's what we're doing with our cars that's probably more of a worry. Not just because of toxic things in gasoline, but just the CO2 itself. Here's some data from how many cars we have in Missoula, how many miles on average they get, what the other things you need are for doing a stoichiometry problem. So really what I have them do is a stoichiometry problem for how much CO2 is released by drivers in Missoula each day, as opposed to what comes from the pulp mill. And this is fossil fuel CO2, so it's not the good kind. The last step of the calculation reveals that on average we're releasing 1,300,000 pounds of CO2 a day into the atmosphere. And Missoula is a small city. It's only about 100,000. Think what much larger cities do in the way of releasing fossil fuel CO2 into the air. Another theme that I use in my class is cyanide heap leaching. Montana has been based on extractive industries. A lot of families of my students are in extractive industries, and I like to help them understand some of the science behind that. This is a picture of the Zortman-Landusky mine in north central Montana that uses cyanide heap leaching to recover gold from gold ore. Some concepts that I get to cover with this particular topic include triple bonds in the cyanide group. That's from chapter 2. Limiting reagent. Limiting reagent is going to turn out to be gold, no surprise. Percent composition by weight. Parts per billion from chapter 6. and sensor add-ins that don't normally get talked about in a chemistry course: water quality standards, which include total maximum daily loads, acute versus chronic toxicity standards, acid mine drainage. So see, here's another disciplinary rich topic. It leads to lots of different tie-ins with the course, and I get to visit it quite a few times. Here's what it looks like in Chapter 4. In the last decade, Montana has gone through 2 rounds of banning traditional use of cyanide heap leaching to recover gold from ores. But cyanide is toxic. It sits on the same part of the hemoglobin molecule as oxygen wants to sit on. And even though you're breathing oxygen, if there's cyanide there, the cyanide won't let go. That's why it's used in gas chambers in states that practice capital punishment by sending convicted prisoners to the gas chamber. They essentially suffocate even though they're breathing oxygen. By breathing in the cyanide, the oxygen can't get to the hemoglobin. Well, here's the chemical reaction for the cyanide heap leach reaction. Gold is essentially dissolved out by using a cyanide containing salt, potassium cyanide. Also includes water and oxygen. So let's see what we're going to run out of first. Let's pretend that we have 100 grams of each of the 4 ingredients. Which one of them are we going to run out of first? That's what we do in limiting reagent calculations. What I have the students do is walk through with me to see how many moles of each of these we have. Remember, recipes are written in terms of moles. The recipe says 4 moles of gold react with 8 moles of potassium cyanide, 1 mole of oxygen, and 2 moles of water. So we have to know how many moles of each of these things we have. We base everything on how much of one of the products we can make. And for this example, I just picked the first product. That's going to be B in our stoichiometry calculations. So if we have 100 grams of gold, we change it into moles using its atomic weight. And then if we know how many moles of gold we have the same number of moles of our dissolved gold species. So we have about half a mole. If we've got 100 grams of gold, that'll make about half a mole of our product. If you do this same sort of calculation for the other 3 ingredients, you'll see that the one that we can make the fewest batches of dissolved gold with is the gold itself. It's the limiting reagent. So there I did a nice limiting reagent sample problem with one of the issues that I feature in the course. Later on, I say, well, let's look at the recipe for that cyanide heap leach solution. You put a pound of sodium cyanide into a ton of water. And that's what you use as your leach solution. Doesn't sound very concentrated, does it? Let's do a weight percent calculation. So we've been doing some of these calculations, and here we'll do another example of it. We take the mass of the solute, divide by the mass of the solution, making sure that the units are the same. And it says that cyanide heap leach solution is 0.05% sodium cyanide. Well, the water quality laws for Montana don't allow just any amount of cyanide in the water, but it's just cyanide, not sodium cyanide, so we have to refine this a little bit. We want to throw out the sodium part of it. Let's see, in sodium cyanide, 26 grams out of 49 belong to the cyanide part. So what we want is 26/49ths of this concentration. If we put that correction factor in, turns out that the cyanide heap solution is 0.027%. Again, it sounds kind of low, but what do the water quality standards say? We can change it into the same units as the water quality standards if we convert it to parts per million. To do that, all we have to do is change it from parts per 100, which is what percentage is, into parts per billion. Instead of multiplying by 100, we multiply by a billion. Only moves the decimal point when we convert the cyanide heap solution to parts per billion. Ooh, it turns out to be 270,000 parts per billion. That sounds pretty high now, if that's the unit that the water quality standards are written in. What does it say in the water quality standards? Ooh, it better not be 200, or it's not good for humans. 270,000 compared to 200. Ooh, it's 1,000 times too high for humans to be drinking. How about for critters that live in the streams? That's what the acute aquatic life standard is for. Ooh, you can only have 22. Looks like we're too big by a factor of not 1,000, but 10,000. And how about for a critter that has to live there 24/7? That's what the chronic aquatic life standard is. We can have even less, only 5 parts per billion. So you can see that the cyanide heap leach solution is way too concentrated to be good for people or critters. And that's why voters in the state turned it down. If you'd like to read more about how I've taken my courses and woven these SENCER themes into them, I have written 2 articles about them. I also show you how I get the students involved in civic engagement activities to earn extra credit in the course by taking action in some of these areas. So I've published a couple of papers about my SENCERize Chemistry 121 course. One of them is in an American Chemical Society Symposium Series book that came out in 2013, and the other one is an article in the summer 2004 issue of Liberal Education. If you want to send me an email for digital copies of these, here's my email address. It's just my name, garon.smith@umontana.edu. Here's a picture of the cover of the American Chemical Society Symposium Series book. My chapter is number 7. It's called Bringing SENCER Civic Engagement Strengths to Large Research Universities, a Trojan Horse hybrid model to initiate incremental course reform. The paper from Liberal Education describes how I entice my students into performing out-of-class civic engagement activities for points they can add on to their exam scores. So both of those are available to you. I think that's all I had for today's webinar. So with that, I'll say goodbye and thank you for joining in.